Good afternoon. This is November 10th, Venture College, TELE 1022 Telecommunications. Okay, this is week 9 of this course, 9 of 14. All right, so today we'll be talking about, well, I can see what's going on here. The antennas. And first, let's start with something like this. I'm not sure if did you guys take the guys and gals? Did you take the tools and safety 1051, SFTY 1051? I don't remember having you there, but we did a little bit. No, I don't think so, but no big deal. So here is what I'm going to. All right, so here is a conductor, all right? And let's say we're going to connect something that's called a clamp meter around it. All right. Now, a clamp meter has a sensor that it's a coil inside that little assembly there. And the assembly and the coil that is inside is wrapped around the conductor. Now, when there's a current going through a conductor, there is going to be, well, electric field, and there is going to be a magnetic field. Electric field is going to be in line with the current flowing. And the magnetic field is going to spin just like that around the conductor. Now, that clamp meter is going to measure the strength of that magnetic field, and based on that, it is going to give you some sort of a number corresponding to the strength of the current, of the value of the current that flows through the conductor. Well, if we have another conductor right beside, and if we clamp on both of them, even though the current is flowing, because let's say we have some sort of a power supply on one end and some sort of a receiver, let's say a light bulb, we can see that the light bulb is on, so we know the current is flowing through that, but the meter is going to show us 0. It is because the other conductor is going to have the same amount of current, causing the same amount of magnetic field, and that magnetic field is just going to spin the other way, all right? The other way with the same strength. So the two magnetic fields, both at the same place, both at the same time, both with the same strength, they're going to cancel each other, and the meter is going to show 0. So the meter, the clamp meter or clamp-on meter should be clamped on only one single conductor in order to measure the current. All right, so those at this, let's say, at this one point, one spot, let's just make it like that. All right, at that one spot, this magnetic fields for both of those fields are going to be canceling each other. They're going to be at opposite phase. If one goes that way, let's say this is a AC current going to make it more interesting, and that's going to be on one conductor. Let's say this is the red one here, all right? And on the blue one, we're going to have the same thing, but with the opposite 180 degrees out of phase. Okay. So at any given point, if this is x-axis And this is the y-axis. This is a time domain. And this is whatever the value x. Well, let's say this is x is the current of I. Then at any of the given point, the average, well, this should be like right on here, okay? At any instantaneous point anyway, if you draw a vertical line here, the sum of those is going to be zero, so they're going to cancel each other. The interesting thing will begin when we take that and separate it this way here, and take the other one and bend it out this way. Now, depending on how long that is, and depending on what frequency that is, so from here to here is the wavelength. All right, from here to here, we got a full cycle, and that gives us the wavelength of this, well, current values or magnetic field strengths. They're just going to be pointed at different directions. The magnetic fields and the electric field are going to be perpendicular to each other. So the electric field is going to be going back and forth here if this is a AC source that we have on this side. And the magnetic fields are going to also build around these two bent out rods or the arms. And if we make the length from here to here, this length, the magnitude of this length, half, here's the lambda, half of the wavelength, we're going to have something like this building, and the other way, okay? So this here would be, from here to here would be lambda, should be lambda here, quarter of the wavelength, and both of them are going to be half of the wavelength together. Then interesting thing is going to happen. The magnetic field is going to start propagating away from the radial. And this is how the simple antenna is made. That's the principle of that. And those waves are going to travel in all directions. So this is going to go this way. It's going to go this way. It's going to go that way, in some sort of like a spherical way, in all directions, horizontally. Okay. All right. So here comes the topic of antennas. Transmit and receive antennas. So an antenna is a conductor or a system of conductors that transition electrical energy to electromagnetic wave in free space. So we can just say that the antenna is a transducer because it conveys electric signals into electromagnetic waves that can travel in a free space. Well, awesome, because if we put another antenna yeah. If we have one antenna like this, I should change the color here to something normal. If we have one antenna going up this way and it's going to propagate the magnetic waves of different strengths. They're just going to collapse and build, collapse and build. So it's going to go up and down here in our 2D drawing. And if we have another antenna here somewhere, and if those waves, still curved, are going to hit that antenna, those magnetic fields are going to induce electric fields, because with the electromagnetic fields, the beauty of that is one induces another. So if a magnetic field hits a wire, it's going to cause current flow. If a current flows through a wire, it's going to cause magnetic field propagate. So here is a transmitter. Here's a receiver. All right. And when the wave hits, and if they start building and collapsing around those two radials, that this thing is positioned at the same polarity as far as physical polarity, then those magnetic waves, those magnetic fields that are going to hit this antenna, of course, the magnetic field is going to be strong here. And as it propagates, it's going to get weak and weak and weak, but still strong enough to induce very subtle movements in the antenna, which we can amplify with a bunch of amplifiers and whatnot, and we can receive the signal. So that's the beauty of this free space communication. Now, I just pointed out that I'm getting ahead of myself a little bit here, but why not? You're going to get hit with this thing again as we go along. You see, if we have one antenna going this way and propagating the magnetic waves or electromagnetic waves, and the other one is positioned in the same way, then you're going to have a very strong reception. If, on the other hand, if you position that horizontally, then those magnetic waves are going to try to build and collapse this way, and those two radials, those two arms, are not going to have enough positioning to actually catch that. So this is called a polarity. There's vertical polarity, and the vertical polarity aligns with the electric field, the current going this way, and that way, just going up and down this way here. So if this other receiver antenna is positioned the same way, that is going to receive those movements, those electromagnetic field changes, and it's going to induce little subtle current there. Okay. So that's the principle here. All right. So for transmitting antenna, the antenna appears as a load at the end of the transmission line that it is connected to. So we could have let's say, coaxial cable, and if we connect that antenna to the end of the coaxial cable, that is going to be a load, just like a resistor to a DC environment. To the AC, this is going to actually appear as a load, which means it's going to use that energy to do something, and it's going to act as a transducer. It's going to convert the energy, but the energy is going to be still there. It's going to take the energy and do something with it and propagate out of itself. Okay, so again, for transmitting antennas, the antenna appears as a load at the end of the transmission line that is connected to transmitter. Amplifiers are generally not co-located with antennas, physically located at the same time. However, there is a tendency for a long time right now that they should be as close as possible. So the transmitter amplifier should be as close as possible. So the wire or the cable or the transmission line, in other words, is the shortest possible, just to to avoid losses and interference, depending on whether you are on the transmitting or receiving end. So often there's a transmission line, and transmission line, we talked about those. Usually it will be a coaxial cable, or otherwise known as concentric cable. There is a trend to start locating antennas closer to the amplifier. And here's the question: why? Well, the transmission line is just one more element where signal losses can occur when it comes to transmitting end. And also on the receiving end, that also could result, the longer the cable, the due to its resistance, some of the signal might get attenuated. Plus, as we remember, some of the transmission lines, or all of the transmission lines, they do have something that's called a slope, which means they amplify or carry through different frequencies in a different way. However, well, yeah, that would make a difference depending on what kind of a bandwidth you're trying to transmit through that. If it's a wide bandwidth, then yes, some of the frequencies are going to be more efficient traveling through that transmission line, and some of them are going to have hard time getting to the end. So you want to have that transmission line as short as possible, so there's no funny stuff happening, to be scientific about it. All right. Ideally, the antenna's impedance characteristics. So remember we talked about something that's called characteristic impedance. What's a characteristic impedance? Characteristic impedance tells the amplifier how hard or how easy it is to insert a wave into that transmission line. So the length of the total length of the cable does not make a difference on the characteristic impedance, because the wave travels on its own. Once the wave is inserted into the transmission line, it just travels on its own under its own strength. So the impedances should be matched. Yeah. Why do the impedance need to be matched? All right, so here we have, I traveled from right to left. I'm gonna start doing that. I'm gonna continue doing that here. Here's an amplifier which has some sort of impedance on its output, and it is connected to a transmission line that is going to have certain impedance, and the transmission line is going to be connected to the antenna, which also is going to have certain impedance. All those impedances should be matched for the purpose of maximum power transfer. If the impedances are mismatched, funny thing is going to happen. Again, to be scientific. And what is the funny thing that is going to happen? Well, some of the signal, if the impedance is, for example, here's big impedance and here's a small impedance, some of the signal is going to reflect back to the amplifier from that point, in phase or out of phase. However, it's going to reflect back to the amplifier. It's going to hit that. So things are not very favorable in this situation. We want the whole signal to be transferred. And when it comes to receiving end, here's the antenna, and here is the preamplifier or the amplifier, RF amplifier going there. If the impedances are mismatched here, that already weak signal that is being received by the antenna might have a hard time having enough strength, and we're going to have a poor signal to noise ratio, which is going to make the signal weak, if receivable at all. So ideally, if the antenna's impedance characteristics match the transmission line and the resonant frequency of the transmission, which that could be, well, could be a topic of its own, because if you have a broadband, which means your band is the bandwidth of the signal or signals or the channels you're transmitting. If the span of the channels is wide, then you have to have some sort of happy compromise. Okay? So on some of the edges, some of the signal is going to get weaker. The antenna will appear as a resistive load with a maximum power transfer. So if the characteristic impedances match, the antenna is going to appear as a purely resistive load. And that's what we want to accomplish, because then things are going to happen. The energy is going to get into the antenna and it's going to get out of the antenna in the most efficient way. Nothing is going to bounce back into the transmitter, or nothing is going to have a hard time going into the receiver. Receiving antennas convert electromagnetic energy into electrical energy. It's also a transducer, so it's a bidirectional transducer. Antenna can transmit, and antenna can receive, and those are being built in the same way. The transmitting antenna can look exactly the same as the receiving antenna, and that property is called reciprocity. That things are made the same way. The transmitter and the receiver transducers are made in the same way. Is it possible to transmit and receive at the same time on the same frequency at the same location? All right. Well, here's an interesting question. Here's an antenna. Here's an antenna. And it is going to transmit on certain frequency. Frequency F, right? With the unit of hertz. Can it also receive on the same frequency? The first thing that comes to our mind is no, right? I mean, if that thing is using or whatever the equipment to transmit on the same frequency, can it receive on the same frequency, because it's going to work with certain frequency? So how can it receive another frequency to receive, because that is just going to be overpowered, or things are going to bite with each other and whatnot. To our surprise, yes, it is possible. The simplest way would be if you have an antenna that can be of 4 radials. So the transmitting antenna here could be vertical, and it's going to hit these two. Right? All right. Now, if we get another antenna and polarize the other antenna different way, completely horizontal, this way, and that is going to hit these two. And they will have there's so that can be actually going this way. Sorry about the colors, and hit this way here. And this can go this way and hit this thing here. So that's the simplest way. It's not as simple, but uh, going that direction kind of helps. Now, also, if you have channel from certain kind of hertz to a certain amount of hertz, and let's say it's a television channel. Television channel has 6 megahertz of a bandwidth. And over there, there's going to be a carrier, sub-carrier, that would be the luminance. Some of them is going to have audio, left and right, stereo, and synchronization carrier and all that stuff. These are called sub-carriers. So if on the same frequency, you're going to place sub-carriers in different spacing within the bandwidth of that channel, then it's also possible to accomplish a two-way communication on the same frequency, although it's a little bit of a tricky answer, almost on the cheating side, because those subcarriers are, not the same frequency, right? But the bandwidth is the same. All right, we've gone through first slide. Halfway dipole antenna. One pole 2, dipole. Half wave dipole antenna, an electrical length of half of the wavelength, half lambda. So what's a halfway dipole antenna? It's a halfway dipole antenna and electrical length of half waves, and it's made out of 2 quarter wave elements. That's the entrance of the antenna. If the antenna is folded like that, then there's going to be no transmission. But when you start separating those, as we just did, like here, then here is half wave. This part takes care of the quarter wave. That part takes care of other quarter wave. And in that way, things are going to start propagating away, right? So if we consider a two-wire line where magnetic fields cancel each other, that's when things are folded. Remember the clamp meter picture I showed you? Then those fields are 180 degrees apart, and they're going to cancel each other. When you open them, then this happens. So that's what it says. By opening the leads 90 degrees, we can create a half-wave dipole that creates a relatively efficient antenna. Impedance of the half wave is approximately 73 ohms. Resistive at the center. Okay, so over here, we're going to about 73 ohms and about 2,500 ohms at the ends. This holds true only if wavelength is a half wave. So these lengths should be somewhat tuned to the wavelengths that we're going to transmit. This holds true in a half wave. With other lengths, we will have a complex impedance resulting in mismatch. So of course we're approximating the antenna length, because if we want to switch channels, we're not going to adjust exactly to the length of this. So we're having good compromise of approximately that length when we're dealing with things in reality. Radiation patterns. The maximum radiation for halfway dipole is the right angles to the antenna. So here's the antenna, right angle here is going to transmit that way. Again, here's the dipole antenna, right angle, right? So from here, boom, that was the way it travels away from the antenna. The halfway dipole radiation pattern is directional. Unlike the isotropic point source, which is omnidirectional. Here's an isotropic point. It's an imaginary point, ideal point. It only exists in theory, but it helps us with certain calculations. So here's about 60 degrees, approximately 60 degrees of the beam width, depending on the antenna. That over here we have 3 dB signal gain of power. So there will be a 3 dB point right here around that green circle. That's a 3 dB point. And over here is also 3 dB point as far as the power goes. And then as we go out, then the signal strength decreases. And we do have equation for that. All right. So here's an isotropic point where all the energy radiates not in a circle way, but in a spherical way. All equally in all directions, 360 by 360 in a sphere. When it comes to the antenna, this is how the signal propagates out of that one. So that dipole antenna will have directionability. As opposed to the isotropic. You can click on that here later on. In comparison to the isotropic radiator, a halfway dipole antenna exhibits gain in certain directions, but it comes at the expense of reduced gain in other directions, which will be the ends of the antenna. If we have 1 watt of power into the if we feed 1 watt of power into the halfway dipole, it does not mean we're getting free energy. I'll explain what that means. Because of the gain in comparison of to isotropic source, it means that the field strength or the wave front is redistributed. Okay. Which means when we have directivity or directionability, let's say this is 2-dimensional isotropic source. Then the energy is equal all around the wave fronts. Okay, and it just keeps going out of that isotropic source equally. If we have another source as the antenna, we're going to have stronger signal here going this direction. We're going to have not a strong signal going this direction. We're going to have even weaker signal going that direction. And we're going to have pretty much almost no signal going this direction. So yes, what that sentence is trying to explain to us is that the amount of energy that travels away from the source, the total amount of energy, is the same as the total amount of energy that travels out of here, except this one is focused a little bit in a directional type of way. Because we have a stronger signal going that way, we are taking away from the sides a little bit and putting it to the front. So nothing lost, nothing gained. The amount of energy is still the same. We're not getting free energy from anywhere. It's just that we're redirecting it somewhere by taking away from some other directions. Okay. So let's read that again. If we feed 1 watt of power into a halfway dipole, it does not mean we're getting free energy because of the gain in comparison to the isotropic source. It means that the field strength or wave fronts are redistributed in different directions. Antennas are a passive device. What is a passive device? A passive device is a device that doesn't need power to operate. Yes, we are feeding power into it, and the antenna works only on that power that we feed into it. What would be an example of a not passive device, which would be active device? Well, let's say transistor radio. Okay, it has to be powered from some other source in order for the electronics to work inside to do something with the signal that it receives. A laundry machine is an active device. It's not a passive device. A dynamic microphone would be a passive device because it just has a membrane that vibrates, and based on those vibrations, it creates electrical signals. It doesn't need to be connected. It does not need to be connected to any other external power source to make anything inside of it works. Now, condenser mic on the other side is an active device because it needs to be powered because it does have some electronic circuitry inside that microphone. So antennas are a passive device, and just as much as a telescope focusing light, right? They have the ability to focus energy. Another analogy would be a garden hose with a wide area of coverage, a focused stream of water, right? If you direct that water, the same amount of water directed into one direction stream, then that stream is going to be stronger. But all around, things are going to be dry. So same thing with the waves. This can be quite useful in many system designs. We can use this directionality excuse me, to focus. We can use this directionality to focus radiated waves over land rather than on the lake, ocean, or up into the sky. Like if you want to just communicate horizontally, why do we need to transmit signal to the aliens that they don't care that we exist? Right? Or maybe they don't understand what we're saying. So when compared to isotropic radiator, a half-wave antenna has 2.5 dB higher gain than or at the right angles to the antenna. So in certain in the peak direction, okay, it has 2.15 decibels higher gain. We're talking about radiating this thing out, waves out of the antenna, than the isotropic. This gain is referred to as dBi. The I stands for isotropic. Since an isotropic radiator cannot be practically realized, which means practically cannot be built because it exists in theory, ideally, the amount of the antenna's gain is compared to a half-wave dipole antenna, and the dBd term is used. D stands for dipole. And we're going to take a look at next slide in 2 seconds. Transmitter and receiver antennas are in a system do not need to have the same gain, and often the receiving antenna has to have a higher gain because it receives a very small signal and it has to do something with that to boost it and amplify it so the signal can be useful. So let's go back to this one here. Since an isotropic radiator cannot be practically built, the amount of the antenna gain is compared and dBd is used. Okay, so let's see here. I made a little supplementary slide, so that's made a different color. And here's the sentence repeated. An isotropic source is a theoretical radiator. It doesn't exist in reality. It cannot be built. Half-wave antennas are used to reference half-wave antennas are used as a reference standard. What was I trying to say? An isotropic radiator has a constant gain of 1. 0 dB I, which is the isotropic source, in all directions. Regardless of the distance from the source, it's going to have a gain of 0 dBi, which means the signal is as it is. It's an ideal source. We label that gain as dBi. I stands for isotropic. A half-wave dipole, on the other hand, elevates that gain to roughly 2.15 decibels in the direction of its maximum radiation. And where is the direction of its maximum radiation? It's this is the dipole positioned in that way. Remember the 90 degrees? That way, okay? Straight out that way, under 90 degrees, whatever the gain of the antenna is, just add 2.15 dBs, and you're going to have the dBd. All right. Half-wave dipole elevates the gain roughly 2.15 dB in the direction of its maximum radiation. Well, what happens if you have a different angle? Then you have to look at the data sheets published by the manufacturer. And you're going to have to see the plot of the antenna strength. Excuse me. And based on that, you can determine and calculate the strength in any kind of direction. So this is a thing that we have to remember. This 2.15 additional gain focused that way, perpendicular to the dipole, which means there's, well, never mind. Over here. Now, let's talk about something that's called effective radiated power. Effective radiated power. When the gain of the antenna is multiplied by its power input, because, well, the antenna has a certain gain going certain direction, and we're going to feed the signal with certain power. So we're multiplying that gain with the power that we're inserting there. So let's see here. When the gain of the antenna is multiplied by its own input, by its power input, the result is called the effective radiated power, and it stands for as ERP. Effective radiated power. This power level is only applicable in the direction of maximum gain of the antenna. But it's very useful in determining the system gain parameters. Mouthful. The power level is only applicable in the direction of maximum gain. Right. An antenna with 100 watts, you feed 100-watt signal into the antenna, and then antenna has 10, the gain of 10. We'll have the ERP of 1000 watts. You feed 100 watts into the antenna with a gain of 10, you're going to end up with 1000 watts in that direction. If we work with the dBs, the math is a lot simpler since we can just add or subtract gains very easily. Okay, let's see the example here. What is the ERP, effective radiated power, in watts? For a 10-watt transmitter connected to the antenna, gain of 10 decibels. dBd, because it's a dipole, so it's got a gain of 10 dBs. The transmission line loss between the transmitter and the antenna in the transmission line, in the cable. So basically the transmission loss in the cable is 3 decibels. Look, we're losing 3 decibels of power just in the transmission line. What does it mean we're using 3 decibels of power? That means half of the power just goes, steam goes into the whistle. It just goes into the cable. Right. Excuse me. Well, first, we're going to convert the 10 watts into the dBms. What's a dBm? dBm is a dB reference or value with a reference to 1 milliwatt. So it'll be the 10 log of 1 milliwatt of whatever the power is here with the reference to 1 milliwatt. This is 1 milliwatt. All right. So convert the 10 watts that were going in there into the dBms. That is going to give us plus 40 dBms. Then, 10 watts. Here's 10 watts over that. And we're going to take a look at the next slide to kind of go into more detail. The effective radiating power out of that is that power plus 10 of the dBd. So we got 40 dBms plus 10. That is going to give us 50 minus 3 because that's the losses in the cable, and that's going to give us 47 dBms. And dBm is a real number because it was with a reference to 1 milliwatt. Now, if we take the antilog of this equation here, because that here's the 47 is the dBm, equals 10 log of whatever the reference, so that's going to give us 10. No. So take that, and we're going to come up with the 50. And Mr. Bach, what have you done? Bad, Bach. I didn't put the units here. Should be watts. So then a quick reference on the math shows us 6 dBs increase. So we know that 6 decibels increase is 4 times the power, because 3 decibels increase is twice the power. 6 decibel is 4 times the power. So 10 watts, 6 by 6 dBs is going to give us 40. How do we get the 6 dBs? Well, we don't. We're getting 7 dBs because we have the gain of 10 minus 3 that we're losing on the transmission power. So we're getting 7. So if 6 is going to give us about 40, then 50 cannot make sense. So that's how you check that with the 7. And this is where it says here, how do we get the 50.12, 50.12 watts? I just put that little explanation how we got that. 47, 10 log P, because that's, we know that's the 47 dBms. That means it's because we're getting power, so we're getting 10 log. If we voltage, that would be 20, but it's 10 because it's power. 10 log of the whatever the reference that we're trying to get, whatever the power, because we're going, what's the ERP in watts? That's what they're that's what we're being asked for. So we want to get that P here, that power. So isolate the log, take the 10, bring it to another side. That's what we end up with. Then that's basically here 4.7. So Then eliminate the logarithm by raising both to the power of 10. As it was of the power of 10. So here, that's what we're going to get. And then from here is just the straight road to get to that 50.118, so 50.12 watts. Yeah. Now, this is a pre-slide to the next slide. VHF, very high frequency, what we're calling it, is a band between 30 megahertz to about 300 megahertz, and the wavelengths from 10 meters to 1 meter. Higher the frequency, the shorter the wavelength, of course. Excuse me. Talking too much. Sip of coffee. UHF ultra high frequency is from 300 megahertz to 3 gigahertz, and here's the length. And microwave is anywhere from 0.3 gigahertz to 300 gigahertz. And the length of it is, well, look, 1 meter to 1 millimeter of a wavelength. That's microwave. All right. EIRP, effective radiated power, effective isotropic radiated power. All right. For the VHF and the UHF frequency ranges, ERP is normally used. But for the microwave systems, the effective isotropic radiated power is used because of the smaller wavelength that look kind of closer to being isotropic source. So we have to take an account for that. Different waves have a different behavior. So we get another 2.15 dBs. EIRP, effective isotropic. No, we don't actually. We just go back to it. Equals ERP plus 2.5, 2.15 dB. So here's the formula here. In order to do a system design using transmitter and receiver, we need to know what received power in the system will be. We need to know what power we have to have on the receiving end, as well as the receiver sensitivity, which tells us how well it performs with a low signal strength. Received power is given by the following formula, and it's not specific to the antenna type, only to the gain characteristics. So here is that PR, which stands for the power received in watts, equals to P, right, over the 16. And here are the explanations. The PT right here stands for the transmitted power in watts. GT, transmitting antenna gain. And it's a gain ratio, not a dB. Compared to the isotropic radiator. So here's GR, receiving antenna gain, ratio, not a dB level. Compare it to an isotropic radiator. Here's lambda, stands for wavelength, and it's in meters. And here's the distance between the antennas, and it's also in meters. And here's that formula that you can do things by hand. You can plug it into Excel, or you can do whatever you need to do to get the results while you're designing a system. Here's some more explanations on how to calculate the wavelength from the frequency. The frequency equals speed over the wavelength. Wavelength was speed over frequency, da 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 da. And here's wavelength in meters, frequency, and here's that letter mu in seconds, and here is the speed of light. So that's just a little kind of a thing. I had to throw it in. All right, here we're going to have an example. Two halfway dipoles are separated by 50 kilometers. The transmitter feeds the antenna with 10 watts at the frequency of 144 megahertz. 144 megahertz. Now we're looking with the, well, we are within the VHF here. Calculate the power and the voltage received, assuming a 73 ohm system. We assume that the dipoles are aligned for the minimal loss, so the dipoles are aligned. All right, gain of the dipoles is gain of the dipoles is 2.15 dBs compared to the isotropic source, and the gain ratio is anti-log of the 2.5 dBs. So the gain ratio is going to be the 1.64, and this is how I got that here. Right? We can later on you can just analyze this, right? Because we're getting the all right. The transmitter feeds the 10 watts for calculate the power and the voltage and assume that the dipoles are aligned. For the gain of the dipoles compared to the isotropic source, that's going to be that. So the gain of the dipoles, we need to have the gain of the dipoles to plug in to this formula right here. The gain of the antenna, transmitting antenna here. Gain ratio is da da da, so no units are because it's a ratio, so we have 1.64 gain here. So we plug in those numbers into that formula right here. Actually, here's the formula. Transmitted, 10 watts. Gain of the transmitter, we got the 1.64 because it's the gain of the dipoles. Here's the gain of the receiving antenna, also is going to be 164. So we have that's we're going to end up with the lambda squared, so that will be the wavelength of the we're going to calculate the wavelength of the waveform right here. That's where we got that from. Times 144 megahertz, so that's over that. Okay, so that's right here, and this here you gotta look at it probably 1700 times to get that this here is the wavelength, and it's squared because that's formula the formula tells us so. 16 pi squared times distance 50 kilometers, 50 times 1,000 meters. That's our distance. 16 squared pi, I got it there. That's going to give us power at the receiving end. It's going to give us 2.96 times 10 to the negative 10 watts. Whoa. That's a very small amount of watts, right? What do we have? Well, we're trying to calculate the power and the voltage. All right, V squared R. We're having 73 ohm system. Is the voltage. So here's a square root of that. So here is derived voltage from this formula from V squared R. And you see the current going back and forth, the voltage going back and forth across those dipoles. Look, it's going to be 147 microvolts across the antenna. And that antenna still is able to feed the signal into the radio frequency amplifier or whatever the detection circuitry is there, and strip away the intelligence from the carrier, and you can listen to your radio that way. This would be considered a very strong signal for most receivers. Most system designs allow for a margin of 10 to 15 dBs to account for the weather, misalignment of the antennas, interference, or overall system losses that tend to increase over time. All right, I know I went through this thing kind of chaotically, but this one here, you're just going to have to kind of get yourself a good cup of coffee and sit over it a little bit until you get that thing into your head. Excuse me. Polar plots for antennas. In order to understand the antenna performance and select an antenna for an application, polar radiation plots are used to give full indication of radiation patterns in 3 dimensions. Manufacturer published plots are critical to any data. Okay, that's very important. It basically says. The outside circle labeled 0 dB represents maximum gain. And typically is located at the 0 degree reference. Now, here's your 0 dBs. There are usually 2 views of elevation, an elevation view, which would be the side or horizontal view, and azimuth, the top looking. So elevation, side view, you will be standing here looking at this tall building, which is acting as an antenna, and you'll be seeing patterns like this. Do we have that thing somewhere here? Here. And, excuse me, over here is the azimuth, which is the view from the top, looking down. Which is if you were looking at that donut from the top, you would see a circle like that. How do you like my clicky clicks on my keyboard? I got that dragon something keyboard. Anyways, because it reminds me of Commodore 64 when I was young. And beautiful. No, I'm just beautiful. There you go. Where are we here? There are usually two views, elevation, da, da, da. The antenna plot below is a half-wave dipole mounted vertically, yeah, and which is called a vertical polarization. How do we remember what's vertically? Well, vertically or horizontally, this is how you physically mount the dipoles. If you put them that they stand up and they extend from top to bottom or from bottom to top, then it's a vertical positioning. If they are extending left to right, that's a horizontal position. Also, we go with the horizontal or vertical with the positioning or polarity, it's called. It's aligned with the electric field because the current flows back and forth. It's just kind of vibrates within that, with those rods of the antenna along the rods, along the poles. So that's where the electric field goes. It's aligned with the current and the voltage. And the magnetic field is going to be perpendicular to it. So here is the electric field going that way, which makes those waves that way, go that way. And this thing here goes top and bottom, which makes those waves propagate the other way. All right. So the antenna plot is below halfway mounted. It's called vertical polarization, and maximum gain in direction is at the right angles to the antenna. Transmit and receive antennas must have the same polarization. We talked about that in the very beginning. This is suitable for wide area broadcast. If the antenna was mounted vertically, there would be a maximum gain in just two directions, which that's what we have. Horizontal polarization mass is the most common for TV broadcasting. Although, well, because you want to have the in all directions, the signal going on that directions. If you have vertical polarization, yes, you could have with the TV, but that would be more directional, like regional TV kind of thing. But the wide broadcast, the TV antenna is going to be positioned horizontally. All right, here is a Yagi antenna. Get a sip of coffee. An antenna array, which is antenna that consists of more than one element. That's the array here. An antenna array has more than one element or component. Wow. I just said that. Added elements are often non-driven. Added elements are often non-driven. There's one active element and the other ones are just sort of not connected, but they play important role. Like, for example, if you have a light bulb or a flashlight or a car headlight. So, what am I doing here? All right. Let's say here is a light bulb looking from the top. Here's the filament, okay. It is going to broadcast the light in all directions. Okay. But if we put a reflector here, then the beam from here, the mode or the beam is going to go this way. That was going to go that way. That was going to go that way. Let's extend the reflector here. And that was going to go, oh, it's going to go that way. This one is going to reflect, it's going to go that way. This one is reflect, it's going to go that way. So now we have a directed light. That reflector here is not an active component, which means it is not electrically connected to anything. It's just placed beside, within the vicinity of the light source, which is the active component, which is the one that works. This one is just a reflector. So same thing with those Yagi antennas. Has more than one element, and let's say the added elements, which would be the reflector of the light bulb, are non-driven, not connected to the transmission line. And they help to increase the gain. Help increase the gain. Because if the reflector wasn't there, those beams in that direction would not exist. They would just go that direction, which we don't want. But we want as much as possible here. So the gain of the whole system is increased by having that reflector here, and as those beams are the reflect, they add on to the total strength of the whole content going this way, which we want. Right, added elements are often non-driven, not connected to, and help increase the gain, improve the bandwidth, or other characteristics that are desired. That's my fan. A Yagi antenna uses a reflector and a director element. So look, here is the driven element. Here's the Yagi antenna. Here's the driven element. These are the dipoles here. Here's the reflector. The beams of the energy, they bounce off of that just like the light bounces off the reflector. And then they go that way because that's where we want. And those are the director that just they are used, they serve as kind of like a catalyst for the waveforms to have easier time to form that way and go that way. Pretty cool. It's just like if you had a reflector here, if there's a light bulb, a reflector, and a little bit of a tinfoil tube that would just help the light, shoot the light that way. Or a bunch of lenses that concentrate the light going that way. Lenses are the better analogy. Here's the whole philosophy of Yagi antenna. Is this antenna vertically or horizontally mounted? Well, and here is the pattern of radiation used by antenna. If you look at some of the patterns for microphones that are very similar, for some that's called cardioid microphones, directional microphones. You got 12 dB gain going that way here, and just minus 3 dB going that way. So that's a pretty good, considering 3 dB is half the power or double the power. And you're going to have a couple of ears here or side lobes. But this is the main pattern that you're getting out there. Here's the driven element. Quarter of a wavelength here, quarter of a wavelength here. Altogether, no, sorry, that's a half wavelength here. Yeah. And then, okay, then there's quarter of a wavelength here, the distance. And there's a halfway here, a wavelength. So it's a dipole. And the reflector reflects. And here's a 0.45 length of the wavelength. And here you have a Yagi antenna. You want to know more? There you go. I think that's our textbook that you can buy. Is this antenna below a television antenna? If you are still awake, I know I'm awake because I'm drinking coffee here. I guess nobody's awake. Anybody has idea? Anybody? Has anybody at all? Okay. What was the movie with that teacher? Uh, no. Yeah, Ethan. Thank you. Well, mostly not. It could serve as some kind of a specific situation. Is it able to transmit TV signal? Yes. But usually we don't transmit because it would be directional. And TVs usually are broadcasting all around. Ooh, here is a parabolic reflector. Mm, all right. Remember that formula? Uh, y equals I think it was something like that, ax squared plus bx plus c. Remember that equation? Anybody remember that equation? What would be yeah, Adolfo. There we go. Uh, all right. If C is 0, we would get something like that, right? Hmm. This thing is called parabola. Remember that? There we go. What do parabolas have that is quite useful? Maximum, minimum, yeah, okay. Deviation. There's one thing that is quite useful, and it's somewhere about here. Somewhere here. What would that be called? Focal point. There we go. It just so happened that this is a very, very useful thing. And that focal point has been discovered many, many years ago. And it was, used in, for example, churches. The church would have there would be a church, let's say here. Okay. And of course, there will be some transepts here, transepts there, da da da. Somewhere here. This will be bigger because usually there will be signs of cross as far as but the building. Now, over here would be the altar. And look at this. If you look at some of the old European architecture, and there would be the altar, the priest who will be standing, he will be standing here, and he will be facing this way. That was the old Latin Mass. Okay. You look at the history. What happens? Well, hundreds of years ago, electricity was not discovered, but the acoustics were discovered. So the priest would be talking here, and his voice would be reflecting here here, here. Anywhere it hits from the focal point, it just goes and amplifies in that straight line. So the concentricity of the beam is awesome. And you don't need any power. You could have hundreds of people here in the congregation, and the priest's voice would be carried. Now, in my old town in Poland, there's a church that is like almost 1,000 years old. And as kids, we discovered something, because yes, there will be some transepts here. If you were standing here, and if you were standing here, you would have you have to speak loud to understand each other's what you're saying. But if you were standing here, and if somebody was standing here, you could whisper and you could hear what the other person is saying. Amazing acoustics, because that was also supported with the ceiling and everything else. So acoustic, but we're talking about the parabola. Yeah. All right. Look at this. Whoa. Okay. Also, if you had another area like this and another person standing here, guess what? That person could whisper and this person could hear. And this person could whisper that direction, yeah, and that person could hear. Over there. Well, we have parabolic dishes. Cool, eh? All right, so parabolic reflector. So here's the focal point, and in that focal point, now look, where's the here, microwaves, 1 meter to 1 millimeter. Look at that. How long does the dipole have to be if the wave length is 1 centimeter? Right? So that's where the whole thing happens. Here is a transmitter. We could put a transmitter pointed in this direction here. And wherever it hits, it's going to transmit that way. Wherever it hits, it's going to transmit that way. Wherever it hits, it's going to transmit that way. Huge, huge gain advantage. And almost razor blade sharp directionality. So let's say what the text says here. This type of design can be used at lower frequencies, but it can be used at lower frequencies, and it is. How low the frequencies comparing to a microwave is a human voice? Well, much lower, and it's being used. So can it be used within other wavelengths? Look how big that church is. You think you're going to be able to install that a dish this big? If there's a person who's a huge church, you think you can install a dish that big outside your window? So at some lower frequencies, things are not being done that way because the dish will have to be a little bit bigger. But when it comes to high frequencies with short wavelength, 0.5 centimeter, 5 millimeters, yeah. Now, just a question here. When I move this chat line here, I'm going to move that window right to this here. Did you just see me roll up the window here or not? No, okay. It's just on my screen. Ah, good to know. All right, so this type of design can be used at lower frequencies, but due to the size of the dish, it's typically used only above 2 gigahertz. This design is capable of very high gain and can have a very narrow beam, making it hard to focus. A dish needs to be at least 10 wavelengths in diameter. Hmm? So the diameter, take 10 wavelengths. Diameter versus radius. It is ideal for point-to-point communications. Point to point, no problem. You just have to align those damn things. That's why years ago we used to get those Bell Canada dishes and da da da. Can you come over and install my dish? So you would know where exactly where the satellite is, and you would get a wave strength meter connected to the dish and align it and see if the signal is there. Crank those bolts and nuts and don't breathe on it. Don't move it. Right? Now those dishes are not as popular because internet has. But then again, still some of the in the rural areas you have satellite dish internet, so that has to be pointing at the satellite somewhere in the sky, and you don't have much room to play with, so you just have to find it. So sometimes it's it would be a bit of a headache to find that satellite with that dish, but it was possible to do that. Okay, it is ideal to point to often cellular. Okay, it is ideal for point-to-point communication, often seen on cellular towers. So the towers can communicate with each other. Yes, the disadvantage of that is that you have to really, really align it. But that means you're not polluting anything else. So you can have a better, cleaner transmission from one end to another, point to point. It's almost like having a cable going from one place to another, but not cable. It's wireless cable. All right. Uh, it's ideal when often use cellular towers for link connections, so the towers can communicate between each other. There's several ways to feed this type of antenna, but the most common method is shown below, with the pickup antenna and the amplifier located at the focal point. That's the whole thing. Oof. All right. Parabolic reflector antenna calculations. The gain of the parabolic reflector antenna or microwave dish antenna, as it's often called, can be calculated per below. The gain can be calculated like this. Yeah. Phew. All right. A parabolic dish is K times pi D squared. And here are the explanations. Here's the gain, the antenna diameter in meters. Here's the D. Look at my red point here. Lambda is the free space wavelength of the carrier frequency. And it's placed right here. So obviously, the bigger the wavelength, carrier frequency, the less of a gain you got. There's a reflection efficiency coefficient, typically 0.4 to 0.7, and that would be given in the specs of the antenna. And I show just like the flashlight, or torch if you're from UK, or a laser pointer. The beam spreads as we get further away from the antenna. So the beam width, it does have a little bit of a spread, and it's 70 lengths of the wave divided by the distance at whatever the distance you're standing here. Um, oh, the beam width here. The antenna diameter in meters, sorry. Diameter, not the distance. We can cut it out in the studio. All right. Example calculations. All right. Calculate the power gain in dBi and the beam width of a microwave dish antenna with a 3-meter mouth diameter when the antenna is used at 10 gigahertz. The efficiency is 0.6. And it's 0.7 degrees. All right. It's a formula. Put those things here and you just gotta go through it. Because if you listening to me kind of saying, reading this thing line by line, yes, you're gonna get simple thing, but it has to be, you have to go over a couple times. With these very high gains and narrow beams, it can be difficult to focus microwave antenna. Even little misalignment can result in a complete transmission loss. If anybody was trying to align the satellite dish, you would know. Important thing, cellular towers and safety. Well, microwaves are being used. There's a reason why you don't stand beside microwave when you're cooking your whatever you're cooking there, your Salisbury steak. All right. In the earlier days, during Second World War, microwaves were kind of being experimented with, usually on the ships with the radars and stuff. Some of the technicians would go and climb the towers with that thing still being on, and a lot of them got blind because of the microwaves. A lot of them got burned because see how quickly it takes to reheat your dinner in the microwave. It is the microwave oven, and it's a microwave transmitter. You're standing beside it, you're getting it, and you're going to have extreme burns to any part of your body, including your brain. So you could just peel off the pole and just fall down, brain dead. So power must be turned off when servicing any of those. I used to work for one of the companies. I was trying it out. They said they were trying me, but I was trying them. I wanted to see if I want to work for them. And once we were driving towards Kitchener, and there's that big service antenna there, tower, as you were driving to Kitchener. And one of my friends said, "You see that tower? We're going to be climbing that in the winter." And I said, "No, we won't." So we didn't. That means I didn't because I wasn't with that company anymore. No, I'm not climbing any of those. However, it's a job. The extreme caution has to be taken. In fact, when I was in college here, we used to have some microwave labs in our telecommunications class, and there was a couple of labs that we had to do the microwave transmission, and that one there was tightly supervised in the Faraday's cage, was tightly supervised by the teacher, be one by one, and he would be watching us like a hawk, just so we accidentally don't hold our hand somewhere close to that equipment there, because you could end up with third-degree burn in no time. Now, look, that's an interesting point. Care must be taken that so I just towers can be made to look more aesthetically. Look, this is, well, is this a real tree or is it artificial tree, something that looks like a tree made into a tower? And here's the tower, so they don't burn it. Towers can be made to look more aesthetically pleasing. However, there are many issues. There are many issues with locating, erecting, and approving tower sites. Hmm. That's what some of the cellular antennas look like. I've installed a couple of those. These are line of sight antennas. Installed some of those between the buildings um, in Toronto. A huge parcel hub, huge, like a small town, and these were those were being used for the mm, local area network, for the computer network communications between buildings to send the signals, so the whole facility can function as one. Um, Usually it's a summer job, and you're in the boom lift. Nobody bothers you, except you can bother your own self if you drive this thing not carefully. You can be catapulted out, but that's a small detail. If you know how to fly it, no problem. Okay. Auto antennas. How many antennas does a car need? Well, 1, 2, 3, 4, 5, 6, 7. Car needs 8 antennas. Okay, good. Next slide. There's a lot of communications going on. Some of them are going through the fiber optics. Some of them are being wireless transmissions. Like, for example, the flat tire valve, the flat tire indicator transmitter that's in the valve, that has to be wireless. You know, you wouldn't go very far without breaking the wire if it was connected with a wire. So, and there's some other things like, look, radio, and there's Wi-Fi and all that stuff. 15 plus approaching 20. Okay, so that's the answer, I guess. Yeah, right. These are the systems that use the antennas, and here's approximate frequencies, and this is whether it's transmitting or not transmitting. Where's my flat tire here? Tire pressure system. Look, it's working at 315 megahertz to 413 megahertz or 434 megahertz, and it's a transmitter. Is it a receiver? Hmm. Well, yeah, because on the other side, uh, the valve transmits and the dashboard receives, right? Okay, there you go. Intravehicular. Okay, there you go. It is. Amateur operator antennas. Amateur radio. Why are so many antennas needed? Why are they visible? There's only one possible answer here. So this guy looks cool. And that's it. For different purposes, there are different antennas. And they're visible because, what, are you going to hide them in a car like that? They have to be exposed to the free space. There are some questions that I would encourage you to answer, and maybe this time finally I'll remember maybe to bring them up when we see each other on, I think, Friday. Yeah, it's Friday. Yeah. In the meantime, the lab, we continue with the amplitude modulation. And we're going to have full hands because that's the second session and we need to finish that. And after that, in this case, we're going to do the pre-lab after the lab. Breakfast for dinner. Yeah. That's it for today, guys and gals. We're almost on time, 4:45. We have 5 minutes to go. All right. You can have all that 5 minutes all to yourself. Don't spend it in one time. Have a wonderful rest of the week. And here's Professor Bach signing out. No. Thank you. Thank you. Where's that stop recording? Here it is. Goodbye.